Howdy folks, Mr. K here with a lesson on VSEPR theory. What the heck is VSEPR's theory? What does that stand for? Well, it stands for valence shell electron pair repulsion. Repulsion being the key word in VSEPR. And basically all this adds up to, this repulsion theory, is what are the shapes of molecules? What do they actually look like in three-dimensional space? Before I get into the types of shapes, let's just talk about the main aspects of VSEPR theory. Number one thing is that electrons repel each other. They don't want to be next to each other. Electron pairs repel. They want to stay as far apart as possible. And that's for things being electrons being shared in covalent bonds. They want to stay as far apart as possible. In addition, any unshared pairs of electrons are viewed in the same way. They want to be as far away from everybody as possible. And if a double or triple bond exists, it's viewed in VSEPR as a single bond. I'll explain what that means in just a moment. Now, we've talked about water before, H2O, and that it's an oxygen bonded to two hydrogens, and the oxygen has two pairs of unshared electrons. Remember, this represents a shared pair, and the dots around the oxygen are unshared pairs. Now, this is not what it looks like in three-dimensional space. We draw this on paper to make it easier on us. If I was to draw this in three-dimensional space, it would look more like this. Now the problem here is that I'm representing a three-dimensional object in a two-dimensional format on just this screen. So notice that the hydrogens have gone down to form this bent shape, and the electron pairs have moved up top. Now if you were to look at this in true three-dimensional space, these are coming out of the page at you. These two hydrogens are coming out of the screen at you, and these electron pairs are kind of floating backwards into the screen. If you have trouble visualizing this, remember I have the little models on my desk, so feel free to come by and take a look to get a view of what it looks like in 3D. That's the toughest part about this, is imagining these two-dimensional shapes in three-dimensional space. Now there's several important orientations or VSEPR structures you have to know, and it's all based on the fact that these bonds and unshared electrons want to repel each other. They want to get as far apart as they possibly can without breaking the bond. Because they really want to make the bond, but they don't want to really be close to each other either. So let's go over the one I just gave you, water, right here. Water is referred to as having a bent shape. Oddly enough, it looks like this in three-dimensional space. The two hydrogens are pushed closer together because the push from the unshared electron pairs here is greater. And they want to get as far apart from each other as possible. So whenever a molecule has two pairs of unshared electrons and is making two bonds, it's going to have a bent shape. Now sometimes sometimes you'll have things in a linear shape. For example, carbon dioxide is linear. When we drew the Lewis structure for carbon dioxide, it looked like this. And remember, each oxygen had two pairs of unshared electrons. Now remember, earlier in the video I said that double bonds are treated as single bonds. And these double bonds are really strong. they won't be bent like the water is up here. They want to stay in a flat line. So whenever you have a molecule with a lot of double bonds like this, it's going to have what's referred to as a linear shape. It's going to have a flat line appearance, a 180-degree angle between its bonds. Next up, let's talk about the pyramidal shape. Ammonia, NH3, has a pyramidal shape. Notice that the nitrogen has an unshared pair of electrons and makes 3 bonds to hydrogens. Once again, they want to get as far away from each other as possible, and it's 3-dimensional space. But the push from the unshared electrons is much, much greater than the others. It's similar to bent, except there's 1 less pair of electrons and 1 more bond made. So, like bent, we have the 3 hydrogens, or 3 single bonds, being kind of pushed down by the extremely strong push of the unshared electrons at the top. You notice, if you look at it, it does kind of form a pyramid shape. That's why we call it pyramidal. Linear formed a line, bent formed a bent shape, pyramidal formed a pyramid shape. The last important one that you really have to know is referred to as tetrahedral. In tetrahedral, notice there is no unshared pairs of electrons. It's just 4 bonds. Our example here is methane, CH4. Every time you pass gas, you're passing a little bit of methane. Remember, the prefix for 4 when naming is tetra, and there's 4 things bonded to it. Thus the name tetrahedral. Okay, folks, those are the important VSEPR shapes that you have to know, and how we acquired those VSEPR shapes, what occurred to make that particular shape. I will see you in class.